This is section 2.5, transformations of functions, part 2. So we left off in part 1 talking about transformations and how a shift upward, downward, left, or right looks in the function. And so now we're going to talk about transitions that involve reflecting on the x-axis or reflecting on the y-axis. So reflection on the x-axis in the function will look like a negative in front of the function. And this will flip the function downward. And then a reflection on the y-axis, you'll see a negative inside of the function, and this will flip the function from left to right. So let's actually look at it, because just looking at the definitions can be a bit confusing. Okay. So referring back to the first part of this section, we talked about how if something is occurring in the function, inside of the function, and when we say inside of the function, we're saying that it's grouped with x, then it's going to affect the x's. And so think left and right, right? But if it's not grouped in or housed in with the x, then it's going to affect the y, so think up and down. So in this function right here, this negative in front of it can be a bit misleading because it looks like it's with the x, right? But because it is not grouped in with the x, and what I mean by that is because it is not this, see how it's housed in with the x there? So this is not saying negative x squared, it's saying the negative of x squared, okay? So because of that, this is going to affect my y's. So what we will have is a flip on the x-axis. And think about that, all of my y's that were +1, +2, +3, +4, now they're going to be -1, -2, -3. So this point right here, let me just choose a random point, would be 2, 4, right? If x was 2, so this function right here is y equals x squared. There's our quadratic function. Okay, so if x is 2, then 2 squared would be our output. That would give us 4. But look, now we have 2, -4 for this function, y equals -x squared. Okay, so when that negative is out in front of the function, and what we mean by that is it's not grouped in with x, it's just out in front of it, then we see a reflection upon the x-axis because all of our y's flip, right? And so now all the y's that were positive, like this +4 right here, will now be negative. And in the previous screen, we had it listed as a flip downward, but you could also have something flip upward, right? So as long as you understand that it is going to flip over the x-axis. Okay, so here we go. We have a function of x cubed. So that's our basic cubic function here. Now over here, we have y equals -x cubed. Okay, again, recognizing that this negative is out in front of the function. Because of that, we're going to flip downward. So instead of downward, I'm going to put over the x-axis. Okay, and so that means that, and it looks like it might have been flipped another way, but this is a bit misleading because now this tail right here will be up here, which we see right here, and this tail right here will be down here, which we see right here. So there was a flip over the x-axis because all of my y's that were positive went negative, and all the ones that were negative went positive. Okay, let's look at this. Our function is f of x equals negative absolute value of x plus 2 minus 3. So referring back to the first section, the first part of this section, we talked about when we had addition or subtraction outside the function right here, that would affect our y. So there's going to be a shift up or down, and the shift would be dependent upon the sign. It was true to the sign. So this is going to shift our function down 3 units. And then if there was addition or subtraction inside the function, so housed with x, this would be a left or right shift, and it would be opposite of the sign. So this saying plus 2, well, left or right, that would make me want to go right because it's plus 2. But we're actually going to do the opposite, so left 2. And then this negative out front, it's out front of the function, so it's going to affect the y's. It's going to flip the function downward, or we could say flip over x-axis. I keep putting that backwards. There we go. Okay, so let's talk about how my original function would look. If I had f of x equals absolute value of x, I would have something along the lines of this. But now we have a downward shift of 3, a leftward shift of 2, and then we're flipping it over the x-axis. So I always look at the origin if there's a point there, which in a lot of these basic functions we see that. So shifting down 3, 1, 2, 3, then shifting left 2, 1, 2, and then flipping over the x-axis. So flipping it downward. Let me erase the lines that represented the movement. And that's what we're looking at with my vertex at -2, -3. Okay, graphed, it'll look like this. There it is, entered into the calculator. So this top graph is the function of just absolute value of x, and then that one flipped upside down is after the transformation has occurred. Okay, so that's how it would look graphed on the calculator. If you need guidance on how to put that into the calculator, if you check out section 1 of this 2.5, I actually walk you through that. Okay, so we have f of x equals negative x minus 4 squared minus 3. So I'm going to actually go right into a graph. Well, you know what? Let's talk about it first. This right here would affect my y's, so it's going to be an up or down movement. We said that it's true to the sign when it's outside of the function, so down 3 units. This right here is inside of the function, so it's going to affect my x's. It's a left or right movement, and it's going to be opposite of what the sign tells me to do, right? So we're going to go right 4 units. And then this negative right here out front is outside of the function, so it's going to affect my y's, and I'll have a flip over the x-axis. So if I was just to graph my basic quadratic function of x squared, so just f of x equals x squared, and I got that from looking at this, right? I can see that before those changes occurred, that's what I would have had. I would have something like this. But remember, now we have some shifts going on, so we went down 3 units, 1, 2, 3, right 4 units, 1, 2, 3, 4, and then we flipped it. So we'll have something that looks like this. Graphed in the calculator. We see that same movement. Okay, so see, you can just graph it in your calculator, this type of question, but be careful. You'll want to understand what the calculator is doing. So you'll want to understand why that movement was there, because like we saw in the last video, there are going to be some questions where you will not be able to just put it in your calculator. So go ahead and use your calculator to help you out, but do not rely on it to try to understand it completely. Okay, so this is just some examples of that reflection, but now we're reflecting on the y-axis, so left, right. So notice now, before we had this, right, y equals negative x squared. So because this was out in front of the function, not grouped in with the x, it flipped downward over the x-axis, right? Now this is grouped in with the x, it's housed in with the x. So now it's going to flip over the y-axis. Well, because this is an even function, meaning that there's reflection upon the y-axis, when this side comes over to this side and vice versa, we still get the same looking graph. So don't let that confuse you. It did flip it, it just had symmetry on the y-axis, and so even when it flipped it, it still looked the same. Looking on the second one on the right, we have the square root of negative x being transformed from the square root of x. So first looking here, right, that's the square root of x. And then negative x, square root of negative x. The negative is grouped with the x. It's housed in with the x. Therefore, it's going to affect my x's. And so think left and right. It'll be flipped over the y-axis. And sure enough, it flipped and went out this way instead. Okay, let's consider if it was y equals negative square root of x. Okay, well now the negative is in front of the function. It's not housed in with x. And so it would have been a reflection over the x-axis, right? Because it's affecting the y's, so up and down. It would have been reflected over the x-axis, and it would have been down here. So just navigating through that and really wrapping your mind around what does that exactly mean? Okay, let's talk about stretching and shrinking. So still staying in line with if there's something going on outside of the function, so outside of the portion of the function that is housing the x, right? So if something is going on outside of that, then it's going to affect the y. So we're thinking vertically, up and down. So here we're talking about coefficients in front of there. If there is a coefficient greater than 1 in front of the function, then the function becomes more narrow. So every y value becomes larger, because think about it. If I have a y value that's like 3 and now I'm multiplying it by 2, well, now it's going to become 6. So it's going to become larger, and think about it growing longer and more narrow. If the numerical coefficient is less than 1 in front of the function, then the function becomes wider because every y value becomes smaller. That might seem a little backwards, but think as y's get larger, right, increase in height, so they go higher up on the y-axis, then that's going to narrow out my function. But if I multiplied it by a coefficient less than 1, then my y value is going to decrease, and so it flattens out that function. Okay, so we see that basic function of x squared, and then that's going to be the one in blue, and then we see where there's a coefficient greater than 1 in front of it, 3x squared. So look what happens, it becomes more narrow. And again, at least to me, that at first seemed backwards, because I'm like, hold on, the value is increasing and it's becoming more narrow. What really helped me make that connection was that I was like, oh, it's becoming more narrow because the graph is becoming taller. It's being stretched out vertically. And because of that vertical stretch, think of a rubber band as we vertically stretch it upward, then it would become more narrow. So in the other example, we said that we would have a coefficient that's a value less than 1. And let's say between 0 and 1, so not taking into consideration negative values. So this 1/3 would be a value between 0 and 1. And so notice that the original function x squared is here, and then 1/3 x squared, it widens out. So vertically, it shrunk, widening out. Again, thinking of a rubber band, if I'm holding a rubber band like an O in between my fingers and I squeeze it at the top and the bottom, vertically shrinking it, it's going to flatten out. Okay, so they want us to find the graph of the function. If this was a question in my math lab, they would obviously give you answer choices, graphs to choose from. And so we could just graph this, but let's talk about it before we actually graph it. So what are we seeing here? We see -7, but we see that happening outside of the function. Therefore, it's going to affect the y's. So an up or down movement, and the movement is true to the sign. So since it's -7, it's going to be down 7 units, okay? Then we see -2. That's happening inside of the function housed with the x, so it will affect the x's, but it is not true to its sign. So we are going to either go left or right, if we're affecting x's. And instead of traveling left, which would be towards the negatives, we're going to go right 2 units. Okay, so let's go ahead and graph this and see what we get. So shift 4 to go to my catalog, take it down to ABS for absolute value. Then I'll do x -2, get out of the absolute value, -7. Okay, so look what happened. Here was my absolute value function, which looks like a spread out V, right? It shifted right 2 units, 1, 2, and then it shifted down 7. So I would definitely determine how my graph should move before I graphed it, just in case back here we accidentally put +2 or +7 or just any array of mistakes that you can make, so that if you get a graph and you're like, hold on, that should have moved in the opposite direction, it'll give you just another chance to check your work. Okay, we have f of x equals the square root of x plus 3. So without even graphing this, this is a better example because it actually gives us choices of the graph, so you could see how you're going to see this question in my math lab. But right there, that +3 is happening outside of the function, meaning that it's not housed in here with the x, it's not underneath that radical symbol. And so that +3 is going to affect my y's, up and or down movement. It's true to its sign, so it's going to be up 3 units. So real quick, how would square root of x look? It'd start here from 0, 0 and look something like that. So I'm moving up 3 units. So this 0, 0 point will just go 1, 2, 3. And so we're looking for something that has moved upward. This would not be the case. It moved downward. This one moved to the right, which would be possibly a common mistake, right? If someone says, oh yeah, that's going to move 3 units to the right. This one moved to the left, which could be a mistake if someone said, oh, that's going to affect the x's and it's the opposite sign. And then this one right here, D, we see that it moves up 3 units. Again, we could have put that in our calculator and graphed it, or if you understand that movement, you can just do it that way. This one you could not put in your calculator, and that's why it's important for you to understand the movements that occur when we see the changes in the function. So here they show us y equals f of x. So basically that's the function f of x. And they want us to find g of x, which is f of x plus 2. So I'm going to write that over here. The change here is the plus 2. It's happening inside of the function. It's housed with the x, right? So that's going to be your left or right movement. It is not true to the sign. So instead of moving positively to the right, I'm going to move left 2 units. Okay? That means that all my ordered pairs that are marked out here are going to just move left 2 units. So move that one over 2 units. This bottom one over 2, over 2, over 2, over 2. We connect the dots. And that is the graph I would be looking for out of my answer choices.